In this video, we will be exploring limits graphically. So first of all, the limit of a function is a way to determine the behavior of a function as the value of x gets closer and closer to a certain number, let's say a. So it is the behavior of the function around a, not necessarily an actual point that exists at a. So the notation we will be using is the following, and this reads the limit of the function f at x as x approaches a is L. So we're going to start off with two little investigations with a table of values, with a graph, to explore this meaning of the limit. In the first investigation, we have a rational function f at x equals x squared minus 1 all over x minus 1. We should already know how to graph this, but we will find the limit as x approaches 1, first using a table of values. So I'm going to replace x with 0 in f at x and write down the y coordinate. So when x is 0, y is 1. When x is 0.5, so 0.5 squared minus 1 divided by 0.5 minus 1, I get 1.5. And feel free to pause the video here to complete the table on your own and then come back for the observations. When x is 0.9, y is 1.9. When x is 0.99, so I'm getting even closer to 1, y is 1.99. When x is 0.999, y is 1.999. And then when I actually sub in 1 for x, I get an error. This value does not exist, which we would have known regardless, because for a rational function, any x value that makes the denominator 0 is an undefined value. Whether it's a whole, an asymptote, it does not exist. So as I look from the left side, as I get closer and closer to 1 from the left, the limit as x approaches 1 of f at x is equal to 2. My y value, gets closer to 2. And you'll notice in the notation it says as x approaches 1 with a little negative above. That means as x approaches 1 from the left. Let's continue with the table of values. I'm going to start from 2 and work my way towards 1 from that right side. So when x is 2, y is 3. When x is 1.5, y is 2.5. When it's 1.1, 2.1. 1.01, 2.01. 1.001, 2.001. So as I read my values from the right side, so when x is greater than 1, and I get closer and closer to 1, my y values also approach 2. And this time for the notation, for us to say as x approaches 1 from the right, you will see that little positive above the 1. Now let's check what this means graphically. So let's graph our function f at x. Well, in advanced functions, the first thing we would have done was factor the numerator. X squared minus 1 is a difference of squares, so x plus 1, x minus 1, all over x minus 1. Then we notice x minus 1 is common, so f at x simplifies to x plus 1, where x cannot equal 1. That's a restriction. And because the x minus 1 factors were common to the numerator and the denominator, that means we actually have a whole. And where is that whole? Well, if I replace x with 1 in the simplified equation, the whole is at 1, 2. So let's graph this function. We're graphing a line that has a y-intercept of 1 and a slope of 1, but we will have a whole when x is 1, so right here. And then I'll continue with my slope. Rise 1, run 1. And I'll do the same in the opposite direction. And there's f at x. Now, if we look at this graphically, As x approaches 1 from the left, so here's the left of my function. As I follow this line gets closer and closer to that value of 2 when x is 1. So even though there's a hole there, that's what we're approaching. That is the behavior of the function around 1, whether or not that point exists or not. Now, if I come from the right and I follow this line, I'm getting, again, closer and closer to 2. The fact that these two values, the left side and the right side limits, the fact that they are the same, they are both 2, this means that the overall limit as x approaches 1 of our function is in fact 2. If we had a contradiction there, the limit would not exist. Now, if I were to actually evaluate f at 1, well, there's a hole there. That does not exist. So even though there is a hole at x equals 1, the limit still exists because our function is approaching that value of 2, whether or not it exists. Let's try another example. Here we have g of x equals the square root of 4 minus x squared. We're going to use the table of values approach, and this time we're going to evaluate the limit as x approaches 2. So again, if you want to pause the video to fill in the table of values for yourself, go ahead. Now, when x is 1, y is 1.73. When I sub it in to the square root of 4 minus 1 squared, I get 1.73. When x is 1.5, I get 1.32. When x is 1.9, 0.62. 1.99, I get 0.20. 1.999, I get 0.06. When x is 2, I actually get 0. Okay, well, let's evaluate that limit from the left side. From the left, so when x is less than 2, as I'm following around, my values get smaller and smaller, and then they eventually get closer and closer to 0. And again, from the left, because that little negative is up above. Okay, for the right side, I'm going to start at 3. When I plug in 3, I do not get an answer. And that's because we would have 4 minus 3 squared, so 4 minus 9, which is negative 5, and I can't square root a negative. When I try that for 2.5, 2.1, 2.01, 2.001, I'm going to get the exact same thing. It does not exist. Anything greater than 2, the value does not exist. So now, when I'm trying to take the limit from the right side, the values do not exist. So if the values do not exist, there is no value that we're approaching from the right side of this function. So the limit as x approaches 2 from the right does not exist. Now let's see what this looks like visually. When you see g of x, the square root of 4 minus x squared, it is a semicircle. And let's say I write my function out like this, and I want to clean this up a little bit. Maybe I don't realize it's a semicircle. That's no problem. If you raise both sides to the power of 2, you get y squared equals 4 minus x squared. If you bring the negative x squared over, here you are. This is the equation of a circle with a radius of, well, remember, 4 is r squared, so it's a radius of 2. Now, the fact that our equation was positive square root of, that means we're a semicircle, and it's the top half of my semicircle. So when I graph my function, the circle would be centered at 0, and if the radius is 2, then I'll have a point at 2 and negative 2 on the x-axis, 2 on the y-axis. If it were a full circle, I'd have negative 2 on the y-axis as well, but I only have that top half of the circle. So here's my function. So now let's think about the limits. As x approaches 2, so we're looking here. As x approaches 2 from the left, well, from the left, I'm following the circle, and I'm getting closer and closer to 0. Now, when I'm trying to approach 2 from the right, so from here, there's nothing here for me to latch onto. the function doesn't exist there. So there's nothing to guide me to any value at 2. So in this case, from the right side, the limit does not exist. And because we have this contradiction here, from the left it's 0, from the right it does not exist, the overall limit as x approaches 2 of this function does not exist. Now, if I were to actually evaluate g at 2, I get 0. There is an actual point there, but the limit does not exist. So let's summarize these findings. So for notation, left-hand limit versus right-hand limit, you have the negative or the positive as your superscript. So as x approaches a from the left, you have the negative. As x approaches a from the right, you have the positive. Now, if the limit as x approaches a from the left is equal to the limit as x approaches a from the right of the function, if those match, then the limit as x approaches a exists, and it will be whatever that value they have in common is. If they do not match, then the limit does not exist. And as I've pointed out before, a limit can exist even if there isn't actually a point on the function at x equals a. All right, let's determine each of the following limits. We have graphs here, so we are just reading our graphs and getting familiar with this notation. So first we have the limit as x approaches -1. So -1 is here. This is where we're looking. As x approaches -1 from the left. So from the left, I'm following this function, and as I get closer and closer to x equals -1, my y values are getting closer and closer to 3. Now from the right side, I'm following my polynomial like this, and even from the right side, as x approaches -1, we're getting closer and closer to 3. Because these values match, the limit of f at x as x approaches -1 is in fact 3. For the next one, we have a piecewise function, and we're asked about the limit as x approaches 2. 2 is important here because 2 is where the pieces change from a parabola to a line. So as x approaches 2 from the left, well, from the left side, I'm following the parabola, and as we approach 2, the y value gets closer and closer to, let's say, 1.5. If I'm coming from the right side, I'm following the line, and the line as x approaches 2 gets closer and closer to 4. These are differing values. So the limit of g of x as x approaches 2 does not exist. Okay, final one. I have a square root function, and we're trying to find the limit as x approaches -3. So right here. Okay, as x approaches -3 from the left, I'm following my function, and my function is getting closer and closer to 0. From the right side, there's nothing for me here to latch onto, to guide me to x equals -3. So from the right side, the limit does not exist. And because we have that contradiction there, the overall limit as x approaches -3 does not exist as well. Okay, another piecewise function here. We need to evaluate some limits. Feel free to pause the video to try these out on your own and then come back to check your work. So we're going to start with the limit as x approaches -6 from the right of f at x. All right, -6 is here. I'm coming from the right side. So from the right side, eventually I'd be on this line segment, and the function is approaching 0. The limit of f at x as x approaches -4 from the left side. So -4 is here. I'm coming from the left, so I'm following this line, and as I get closer and closer to -4, y is approaching this point here at 2. As x approaches -2 from the right, so -2 is here. If we're coming from the right, we're following the parabola, and the parabola is approaching 4 as x gets closer to -2. As x approaches -4 again, but this time from the right. If I'm coming from the right and I'm getting to -4, I'm on this line segment, and this line segment is approaching 4. So if I do have to evaluate the limit as x approaches -4 later on, there's a contradiction here. It would not exist. And actually, I see it right here. So I'm going to say it does not exist. Those left side and right side limits contradict themselves. Okay, now the limit as x approaches +6 from the left. So +6 is right here, and I'm approaching from the left. So I'm following, and as I'm getting closer and closer to 6, my function is going to -infinity. So it's not actually a value, but we are going down forever. So technically we can say the limit does not exist because infinity is not an exact number, or we can just say it's -infinity because it's going down forever. As x approaches 1 from the left, so 1 is right here. If we're coming from the left, we're following the parabola, and the parabola is approaching 1. As x approaches 2 from the right, I'm on this line segment here, and I'm approaching that hole when x is 2, so we're approaching 4. As x approaches 0 from the right, well, 0, I'm on the parabola, and we're approaching 0. As x approaches -7, -7 is here, and here we don't have a left side or right side limit, so we have to determine, are the left side and right side limits the same? If they are, the limit will exist. So as x approaches -7, from the left we're getting to -1, and from the right we're getting to -1. So that exists. As x approaches 1, well, as x approaches 1, we have this jump here. So from the left I'd be approaching 1, but from the right I'd be approaching 3. So that does not exist. As x approaches 2, well, for 2, yes, we have a hole, but from the right side we approach 4, and from the left side we approach 4. So that works. We already established the limit as x approaches -4 does not exist because of that jump. The limit as x approaches -2. Well, for -2, right here, from the left side we approach 4, and from the right side we approach 4. So that's good. For 6, we already established that the limit as x approaches 6 from the left is -infinity, but from the right it would be going to +infinity. So there's a contradiction there. So it does not exist. The limit as x approaches 7. 7 is here. There's a point there. From the left side, we're approaching 4, and from the right side, we're approaching 4. And finally, the limit as x approaches 4. Well, at 4, we have a jump here. So from the left side, we're approaching 6, but from the right side, we're approaching approximately 2.5. Those are not the same, so the limit does not exist. So these are all examples where the graphs have been provided for us. But of course, we can be given a function without its graph, and we have to evaluate the limit, which means we should first graph our function using our previous knowledge, and then we can determine those limits. Now, we could also do this with an algebraic approach, but for this video, we're focusing on the graphical approach, and it will allow us to refresh on some graphing skills. So here we have the function g of x, which is made up of all 3 pieces. A parabola when x is less than or equal to -2, a line when x is between -2 and 7, and an exponential when x is greater than or equal to 7. So lots of different ways we can graph. We can just do table of values within those intervals to get some points, graph our function, or we can use our knowledge of properties of the functions or transformations to graph. So for this parabola, I think I'm just going to factor it first, or I can complete the square to go into vertex form. So -x squared plus 8x plus 16, and if we factor that, we would have x plus 4 and x plus 4. So actually, just factoring like this, we actually do have our vertex form. Our vertex is at -4, 0, and that is within our interval of x is less than or equal to -2. So I'm going to plot that point. And then I can also use the step pattern by multiplying 1, 3, 5 by that -1a value. So my step pattern is -1, -3, -5. So I'm going to apply that to the left as much as I can. So there's the left side of the parabola. And for the right side, I'm only going to apply it until I hit -2. And at -2, we do have a point because we are less than or equal to -2. So there we are, parabola is done. Now for the line x minus 2, between x is -2 or 7, we can just plug in values. It is linear, so there is no curvature here. I can start with plugging in -2 to see where the hole would be. So -2 minus 2 is -4, so I can plot the hole at -2, 4. Then I can plug in -1. -1 minus 2 is -3, so -1, -3 is a point. Or I can use my knowledge of y equals mx plus b. The y-intercept is at -2. The slope is 1, so I'm rising 1, running 1. And I can apply this until I hit x equals 7. But when I hit x equals 7, I will put a hole there. Now I'll do the same thing in the opposite direction. And normally I would put a hole here, but there's already a closed point because of the parabola. So I can just connect my line to the parabola directly. But there is a hole for 7, 5. And then finally, for the exponential, because it is past 7, I'm not going to use my transformation knowledge. I mean, I know it is 2 to the power of x as my parent function, and we have to move it to the right 6 units. But because I just have a few points to fill in, I would just do a little table of values or do it in my head. So when x is 7, 7 minus 6 is 1, so 2 to the power of 1 is 2. So I could plot the point 7, 2 as a closed point. Now, if doing it in your head isn't the greatest, just do a little table. So we're going to plug in 7, 8, 9, and 10. So we have 2 to the power of 1, because 7 minus 6. 2 to the power of 2, because 8 minus 6 is 2, so that's 4. 8, 4. 2 to the 3, because 9 minus 6 is 3, that's 8. So 9, 8. And then I'm off my grid for the rest of it. So there we are. And now we're ready to evaluate our limit. So we'll start with the limit as x approaches 7. So from the left side, we're approaching 5, but from the right side, we're approaching 2. So the limit does not exist. And my justification would be those left side, right side limits. So the limit of g of x as x approaches 7 from the left is equal to 5. And that's coming from following the line. And the limit as x approaches 7 from the right of g of x is 2. And that's following the exponential. And that's why it does not exist. Next, the limit as x approaches 1. Well, as we approach 1 from the left, we're approaching -1. And from the right, we're also approaching -1. So that's good. Next, the limit as x approaches -2 of g of x. So from the left, we're approaching -4. And from the right, we're approaching -4, even though it's a change of the piece of the function. So from parabola to line, they're approaching the same value of -4. So the limit exists. And finally, the limit as x approaches -infinity of g of x. So this is asking long term. So for this, as we're approaching -infinity, we're going to the left. So we're on the parabola, and that parabola is going down forever. So -infinity. All right. Our final two examples are graphing, but with absolute functions or absolute value pieces within a rational function. So when we evaluate the limit as x approaches 2 of the absolute value of x minus 2 over x minus 2, if it were just an absolute value function, we'd have no problem graphing this. But the fact that we have the absolute within a rational, we have to rethink our strategy. And what we're going to do is turn this function into a piecewise function. So let's say this piece is f at x. F at x is going to equal 2 pieces. And the 2 intervals are going to be based on when that absolute value in the numerator is 0. So for what x value will x minus 2 from here give us 0? Well, that's 2. 2 minus 2 is 0. So we're going to have 2 pieces, one for when x is less than 2, and one for when x is greater than 2. We will not be equal to 2 because our denominator gives us the restriction that x cannot be 2. So now, if we pick x values that are less than 2, like 0 or 1, when I plug them into my numerator, let's stay 0, 0 minus 2 is a negative number. Now, if I want to remove my absolute value signs, what operation can turn a negative number into a positive? Well, multiplying by -1 turns a negative number positive. So I'm going to take that x minus 2 in the numerator, take off the absolute value signs, and replace them with a multiplication of -1. It does the exact same thing. And then I'll do the same thing when x is greater than 2. If I plug in values greater than 2, like 3 for example, 3 minus 2 is 1. That's a positive number. When x is greater than 2, those absolute value signs are useless. So I'm just going to take them off. And here is our piecewise function to represent this. Now let's clean it up because things can cancel out nicely. Those cancel, those cancel. So when x is less than 2, our function is just -1. And when x is greater than 2, our function is +1. So this function is really just 2 horizontal pieces. When x is less than 2, the function is y is equal to -1. So a horizontal line at -1. So I'm going to put my hole when x is 2 for a y value of -1. And here we are. And when x is greater than 2, there's a hole at 1 and then a horizontal line. And there we are. And now if I want to evaluate the limit, I can clearly see it does not exist. The limit as x approaches 2 from the left of this f at x, well, that's equal to -1. The limit as x approaches 2 from the right of f at x, well, that's +1. That's a contradiction. So therefore, the limit as x approaches 2 of f at x is, well, it does not exist. And there we are. So we're going to do one more example similar to this with those absolute values. So we need to determine the limit as x approaches -1 of x squared minus 1 divided by the absolute value of x plus 1. So first of all, I'm just going to call this function g of x. Now in this function, x cannot be -1 because of that denominator, but also at -1, that's the dividing line between positives and negatives for that absolute value piece. Because when x is -1, -1 plus 1 is 0 in the denominator. Anything greater than that will give us a positive in the denominator. Anything less than that, that x plus 1 will be negative. So let's split off into 2 pieces. So let's start with when x is less than -1. Well, in the numerator, I'm going to turn x squared minus 1 into x plus 1 over x minus 1. And in the denominator, if we plug in a value less than -1, x plus 1 will be negative. How can we fix that and turn it positive? By multiplying it by a negative value. Same thing for the interval when x is greater than -1. My numerator, I will apply that difference of squares. But in the denominator, if x is greater than -1, x plus 1 will be positive already, so I can just drop those absolute value signs. And once again, things cancel out nicely. So here's what we're left with. G of x is equal to, when x is less than -1, we're going to have x minus 1 times -1. So I'll just distribute that in. And when x is greater than -1, we have x minus 1 for our function. So now let's graph it. And we're looking to the left and right of -1. So when we're less than -1, Technically, we would have a y-intercept at +1 here, but that's not part of our interval. And then our slope is -1, so going down 1, right 1, or going up and left from that y-intercept. But that doesn't exist, so I'm not going to plot it. But when I work backwards, I know I'm going to have a hole here at -1, 2. So that I will plot and then continue with that -1 slope. So there's one piece. And when x is greater than -1, our y-intercept is -1 and the slope is positive. So here we are, but also continuing in the other direction, I have a hole at -1, -2. And once again, I have a contradiction in my limits. The limit as x approaches -1 from the left, we're following this piece, and we're approaching 2. The limit as x approaches 1 from the right, or -1 from the right of g of x, well, that's going to -2. So therefore, the limit as x approaches -1 of g of x, it just does not exist again because of that contradiction in the left side and right side limits. And that's it. So as a reminder, when you're evaluating a limit, you're talking about the behavior of the function around that value. And in order for it to exist, the left side and the right side limit have to match, even if the point itself does not exist.